Welcome to the solutions to the college physics springs and simple harmonic motion problem set, problems number 9 through 13. Let's jump right in. Number 9, we have a bunch of conceptual questions here. First, does the period of a pendulum depend on the mass of the bob, the length of the string? Upon what else does the period of the pendulum depend? Well, taking a look at the formula for the period of a pendulum, t equals 2 pi square root. Dependent variable is the length over the constant, which is g. There's our answers to the question, does it depend on the mass of the bob? The answer is no. It is independent of the mass. You could attach anything to the bottom there. Does it depend on the length of the string? The answer is yes. In fact, that's the dependent variable for the period of a pendulum. And upon what else does the period of a pendulum depend? It depends on the acceleration due to gravity. It's constant near the surface of a planet or moon, but obviously can change as you change the location from that. One other point to bring up here is that the period of a pendulum is only applicable and constant during oscillations that are vertical angles of 10 degrees or less. When you get out beyond 10 degrees, you have other components of forces that are acting here that contribute to the period in the pendulum. So our general rule of thumb is that as long as the vertical angle is 10 degrees or less, then this formula applies quite nicely and accurately. Number 10, does the period of a mass on an oscillating spring depend on the mass attached to the spring, the stretch, compression, amplitude of the spring? Upon what else does the period of a pendulum depend? Again, looking at our equation for the period of an oscillating spring, there's a typo here. Upon what else does the period of a oscillating spring depend? Please cross this out if you have it in your notes and change that. But nonetheless, period of an oscillating spring, t equals 2 pi square root. Dependent variable is m over constant, which is the spring constant k. So does the period of a mass of an oscillating spring depend on the mass of the spring? Answer is yes. That is the dependent variable. The stretch, compression, amplitude of the spring? The answer is no. Nowhere in the equation do we see x. And upon what else does the period of an oscillating spring depend? It also depends on the spring constant of the spring itself. All right, number 11. Can a pendulum clock be used in the orbiting International Space Station? And explain. Well, taking a look at the period of a pendulum equation, we have t equals 2 pi square root of L over G. And what we would note here for the orbiting International Space Station is that the contents of the station and whoever's on it are in a constant state of free fall as they're orbiting the Earth. They're constantly falling back towards the Earth during the orbit. What this does is it gives an apparent acceleration due to gravity of 0. That's why the astronauts and objects inside it, if not attached, can appear to be floating around inside as if they're weightless. And that's because the apparent acceleration due to gravity in that scenario is 0. So could a pendulum clock be used in the orbiting International Space Station? The answer is no. The period would end up being negated here because of the acceleration due to gravity equal to 0. All right, number 12. How long must a pendulum be to have a period of 1 second on the Earth? So we're going to start off with the formula for the period of a pendulum. T equals 2 pi square root L over G. We're told that our period is to be 1 second, 2 pi L over 9.81 meters per second squared. Our job is to solve for L. To do this, we would divide 1 by 2 pi. square both sides, and multiply by 9.81. Completing that, we would get an L value of 0.253 meters. So for reference here, if you were stranded and wanted to keep time, if you cut a piece of string 25 centimeters long, that's a quarter of a meter, and attach a mass to it from a pivot point and keep that oscillation 10 degrees or less, you would have your homemade pendulum clock that would be 1 second from one complete oscillation. Number 13, how much mass must be attached to a spring of spring constant 10 newtons per meter so that its period of oscillation is 1 second. Similarly, as the last question here, we're going to go with our period formula for the mass on an oscillating spring. T equals 2 pi square root m over k. Our period is desired to be 1 second. 2 pi square root m over 10.0 newtons per meter. Again, we would divide both sides by 2 pi. We would square both sides to get rid of the square root. And then we would multiply that by 10. And we should get a mass value of 0.253 kilograms. And of course that's 253 grams, just to have you give you perspective there, as you've used the masses quite a bit in class. All right, that'll do it for our solutions to numbers 9 through 13. More to come as we do problem 14 together in class tomorrow.